Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video on prime factorizations. So central to our work here is the fundamental theorem of arithmetic. Any positive whole number greater than 1 can be written uniquely up to order as the product of prime numbers. So what does all that mean? Well, let's just look at an example 72. So I can write 72 as the product of prime numbers. I can write it as a whole heap of prime numbers multiplied together. So it turns out the prime factorization for 72 is 2 to the power of 3 times 3 to the power of 2. Of course, you could also write this as 3 to the power of 2 times 2 cubed because the order of multiplication does not matter. So we say that this is unique up to order. There is no other way that you can write 72 as the product of only prime numbers. These two here are essentially the same. 3 squared times 2 cubed and 2 cubed times 3 squared. They're the same because the order of multiplication doesn't matter. They really are the same thing, and that's what we mean unique up to order. There's only one way that you can write it, but you can write the numbers in a different order. So there's no other way that you can write 72 as a whole heap of prime numbers multiplied together. Of course, 3 squared times 2 cubed is 3 squared is 3 times 3 times 2 cubed. So 2 is a prime number and 3 is a prime number. So you can see here 72 is written as the product of a whole heap of prime numbers. It doesn't matter that the prime numbers are repeated. It turns out that we could do something similar for any positive whole number greater than 1. But just before we look at other numbers, I want us to think, well, how do I actually get to this? How do I find out that the prime factorization of 72 is 2 cubed times 3 squared? And the way we actually do that is with something called a factor tree. What we do is we factorize the number. We write it as something times something, find factors of it, and we keep factorizing. We keep finding smaller and smaller factors until all the factors we have a prime. So that probably sounds a bit confusing, but let's look at what a factor tree looks like. So we start with our number 72. And what we need to do is find two factors of 72. Any two will do. It actually doesn't matter whether I here use 9 times 8 or 12 times 6 or 36 times 2. I will end up getting the same answer when we're done. Don't use 72 and 1, however, because 1 is not a prime number. We're only wanting numbers greater than 1 here. So I'm just going to choose 9 and 8. Again, I could have chosen 12 and 6 or whatever. So 72 is 9 times 8. Now, what you do is keep going until you've got only prime numbers. 9 is not a prime number. So what we do is we factorize 9. So again, we don't want to use the number 1. That really doesn't do anything for us. So 9, if I can't do 9 times 1, I'll do 3 times 3. So note, 3 is a prime number, so I can stop there. But I've still got here an 8. 8 is not a prime number, so I'm going to factorize it. So I can't use 8 and 1, that leaves 4 and 2 as the factors of 8. So I'm almost done. 2 is a prime number, but 4 is not. I factorize it as 2 times 2. So the final thing here, 72 is 3 times 3 times 2 times 2 times 2, which is exactly what we got here. But we write it in index form is a bit simpler. There are 3 2's multiplied together and 2 3's multiplied together. So that is how we did the prime factorization of 72. Now I just want to do 72 again and show you that it doesn't matter which factors you start with. So for 72, I could have gone 12 times 6, but I follow the same process, I'll get the same answer. So 12 is not a prime number, so I factorize it again. Doesn't matter which factors I choose as long as one of them's not 1. So 12 is 4 times 3. So 3 is a prime number, I stop here. 4 is not, I need to factorize it again. So now we go on to 6. 6 is not prime, but I can factorize it as 3 times 2. Once again, you see I have 3 2's multiplied together, which gives me 2 to the power 3, and I have 2 3's multiplied together. So note, 2 to the power 3 times 3 squared is 8 times 9 anyway, which is 72. So that is how you do a prime factorization. So let's look at some other numbers now. So let's say I want to find the prime factorization of 147. So I want to write 147 as a whole heap of prime numbers multiplied together. I don't know how many there will be yet, but that is my goal. So what I do is I start with the number and I factorize it. Now, what we learned a few lessons ago, divisibility tests, they can help here because it's hard to know off the top of your head what is a factor of 147. So it's obviously not even, so it's not divisible by 2. But if we use our divisibility test, 1 plus 4 plus 7 is 12. So the sum of its digits is divisible by 3, so 147 is divisible by 3. So of course, if you need to know what you times by 3 to get 147, just go 3 into 147, short division. 3 into 1 is 0. 3 into 14 is 4, remainder 2. 3 into 27 is 9. So it's 3 times 49. Okay, so 3 is a prime number, but 49 is not. So I need to factorize 49. I can't use 1. There's only one way to factorize it. It is 7 and 7. So 147 is 3 times 7 times 7. In index form, that's 3 times, and there are 2 7s. So I put a little 2 there. 3 times 7 squared is 147. So once again, I've written it as a whole heap of primes multiplied together. So we just take the number and we keep factorizing it until we have prime numbers at the bottom. So that's how we write any number as the product of prime numbers. So let's now use this to find the highest common factor of two numbers. So we can use factor trees to find the highest common factor of two numbers or even more than two numbers. So what we do is we do a factor tree for each number, then we circle the numbers that are common to both trees, hence highest common factor, and if we multiply them together, we get the highest common factor. Let's look at an example. So let's say I want to find the highest common factor of two numbers, let's say 36 and 84. So I'm going to do a factor tree for each. So let's start at 36. Remember, it doesn't matter how you factorize this as long as you don't use 1. So it doesn't matter whether I use 6 times 6, 9 times 4, 12 times 3. I'll end up getting the same answer. So let's do 9 times 4. Okay, so 9's not a prime number. So I need to factorize it. 3 times 3. And I can factorize 4 as 2 times 2. So let's do something similar for 84. Again, doesn't matter which factors I use as long as I don't use 1. I can use 42 times 2, 12 times 7, whatever I want. So in this case, I'm going to do 12 times 7. So 7's a prime number and I stop there, but 12 is not. So 12 is 4 times 3. 3 is a prime, but 4 is not. So I do 2 and 2. Okay? So prime factorizations, 36 is 3 squared times 2 squared. And 84 is 2 squared times 3 times 7. That's the prime factorization of each number. So to find the highest common factor, I've done step 1. Now I circle the numbers in both trees. So both of them have 2 2's, so I'll circle them. Now I can't circle both 3's here because this tree only has 1 3. So I circle 1 3 in both trees. Okay? And you can see 84 has a 7. I don't circle it because it's not common. So I've circled the ones that are in both trees. Now for the third step, I just multiply them together. So the highest common factor is just 3 times 2 times 2, which is 12. 12 is the highest number that goes into 84 that also goes into 36. So this is an example of how we can use factor trees to find the highest common factor of two numbers. So if you're watching this video, the first 3 people in the class who come to me with the code word always, and they mention that it was in the prime factorization video that they heard this, you will get a prize, just to reward people who've been watching the videos. So come to me and say the code word for the prime factorizations video is always, and if you're one of the first 3 to do that, you will get a prize. So thank you so much for watching. This has been the luckiest maths teacher in the world. Have a great day.